Hello there. In this video we're going to lay down the foundations on how to construct confidence intervals for the population variance and the population standard deviation. So let us first develop a couple concepts that are sort of going to help us out. First off, recall that the variance and also the standard deviation are always greater than or equal to 0. So the distribution that we've been pretty much working with mostly is usually a t and a z distribution, which can go to the left and also to the right of 0. So if we want to use t or z here, they're not pretty much going to help us with this type of problem. But there is another distribution that we have discussed, actually a couple, namely the exponential distribution, the chi-square distribution, and a couple others that may be possible conditions that we may want to consider. But before we start guessing things, let us pretty much lay down pretty much what we want to go for. Alright, so let us assume that there exists some distribution. I don't know what this distribution is, but I'm going to call this distribution f. So if I can find out whatever distribution this is, and it's associated to, namely, sigma squared and sigma, then I'm going to find pretty much this interval here. And it may not be symmetric, I don't know. But nonetheless, this is going to be equal to c. And there's going to be these numbers a and b, which we usually call the critical values for this confidence interval. So pretty much once we have this, then we can construct a confidence interval based on that. So pretty much what we're going for is something along these lines. So the probability associated to f, such that sigma squared is in between these two values, a and b, we would like this to be equal to our level of confidence c. And once we have that, then that's pretty much going to guide us into our confidence interval, because a is going to be the left and b is going to be the right. And this process is going to pretty much help us get there. So here's a property that we're going to sort of take advantage of, and we're going to assume that this is true. And the property is this: the random variable x is equal to nu s squared divided by sigma squared is associated to the chi-squared distribution with nu degrees of freedom. And in this case, nu is going to be equal to n minus 1 for a one sample test. So we already know some things about chi-square at least. So we know chi-square has a very non-symmetric but yet smooth distribution. So this is going to be x, and this is going to be our chi-square distribution with nu degrees of freedom. So now we're going to be looking for these two numbers here. And this is going to correspond to our level of confidence c. And this is going to be my left confidence interval critical value. And this is going to be my right value. In some literatures, you may see this notated as chi-square alpha over 2 and chi-square 1 minus alpha over 2. But we're going to use the L and R notation because sometimes it's more simpler to calculate. And keep in mind here, this is non-symmetric. That means once you find one of these critical values, you can't just take the negative of it in order to get the other. Alright, so from this idea, we can pretty much guide ourselves through how to construct a confidence interval. So from this, what do we get? So the probability associated to a chi-square distribution for x is going to be located between chi-square L and chi-square R, and we want this probability to be equal to c. So we already know a variable that's associated to x that follows a chi-square distribution, and that's going to be this property that we have discussed already. And that variable is going to be nu s squared divided by sigma squared is less than or equal to chi-square R. And we want that probability to be equal to c. And just for notation here, sigma squared again is the variance of the population, which is what we're trying to construct a confidence interval for, and s squared is the sample variance for some sample of size n. Alright, so from here, what do we get? So we can divide both sides by nu s squared. Nu is always a positive number since you can't have negative sized samples, and variance is negative because that's defined to be a square root. So what are we going to get? So this probability is going to be equal to chi square L divided by nu s squared is less than or equal to 1 divided by sigma squared is less than or equal to chi square R divided by nu s squared, and this probability is going to be equal to our level of confidence. So I'm then going to take all of our fractions and invert them. So my top is going to go to the bottom, my top is going to go to the bottom, my top is going to go to the bottom, and that's going to put my sigma squared in the numerator, which is going to put my sigma squared in the middle of my confidence interval. So once I do that, keep in mind when you invert all our fractions, my inequalities are going to flip directions. So this is going to become my left boundary for my interval, and this is going to become my right value if we write it from least to greatest. So that's going to give us the probability. So we're going to have nu s squared divided by chi square R is less than or equal to sigma squared is less than or equal to nu s squared divided by chi square L, and this is going to be equal to C. And what we have constructed here is a confidence interval for the population variance. And usually the big assumption here is, the population for X has to be typically normally distributed, and sometimes a couple other things, but we won't go into those details here. All right, so let us write this in a formal notation. So the confidence interval for some level of confidence C for the variance is going to be equal to nu s squared divided by chi square R, comma nu s squared divided by chi square L, and this is going to be our confidence interval, where chi square R and chi square L are my right and left critical values of my confidence interval. So let us assume that you also want to calculate the confidence interval for the population standard deviation. Well, you may already figure out how to do that. We're just going to take the square root of the boundaries of my confidence interval for variance. So that's going to be equal to the square root of nu s squared over chi square R, comma, the square root of nu s squared divided by chi square L. And try not to do any algebra. I don't want you to calculate, cancel the square with the square root on the chi square. Now you may be able to do that for the variance and see the standard deviation, but keep in mind that's going to give you the square root of the degrees of freedom, and sometimes people forget that when they try and substitute it. So just, typically go for the variance confidence interval first and then take the square roots of the boundaries just to be safe. So one last thing, just to be clear, how do you calculate these critical values, chi square L and chi square R? That may be the only tedious part of this calculation. So of course this is going to be a chi-square distribution with nu degrees of freedom, and we want to calculate these critical values. Let's call this chi-square L and chi-square R again. So if this area is C, then this area to the left of C is going to be alpha over 2, and this is going to be alpha over 2. And keep in mind, this is going to be for a hypothesis test of the form. H0 is sigma squared is equal to something for which they hypothesize. And the alternative is that the variance does not equal to that claim. So this is going to be a two-sided alternative. So we're going to have alpha over 2 on the left and alpha over 2 on the right. All right, so if we look at this picture, we can sort of focus on this chi-square L portion. So we can see that the integral from 0 to chi-square L under the chi-square distribution with respect to x is going to be equal to alpha over 2. And if we focus on chi-square R, that's going to be R. Then notice that we have alpha over 2 here, and we have a c value here, so we have alpha over 2 plus c on the left-hand side of that portion. So that means this is the integral from 0 to chi-square r under the chi-square distribution with respect to x. This is going to be equal to alpha over 2 plus c. And if you remember how we, found these values chi-square L and chi-square R before, we usually found the x-intercepts of these corresponding functions. But if you're pretty much comfortable or you're not really focusing on the integral representation and you just want to jump to Excel, you can of course do so. But using these same exact relationships, we can get that chi-square L is going to be equal to CHISQ dot IMV of alpha over 2 the degrees of freedom. And similarly for the chi-square r value, chi-square r is going to be equal to chi-square dot IMV comma alpha over 2 plus c comma v. And some people may rewrite these formulas. For example, this can be written as 1 plus c over 2 is another common equivalent expression for that. And some people may write this other one as 1 minus c over 2. But these, I think, is a little bit more intuitive, so I'll keep them as so. But that's how you calculate your critical values for your variance and your standard deviation confidence intervals. And in the next video, I'll work through a practical example of how to implement these things.